Okay, well, good morning. So today we're going to do a couple major things. One of the most important things we're going to talk about is what's called central tendency. Now that sounds really scary. Actually, central tendency is a fancy way of saying average. Kind of where's the center of a large group? Where does, most of the numbers seem to fall? But before we do that, I want to talk about the graphical representation of some of the data. So today we want to introduce the histogram. The histogram, this is my favorite of all the graphing techniques because from a visual standpoint, I think it's the easiest one to interpret and it tells us the most amount of information. A histogram, just so you know, let me draw you kind of a loose random histogram. A histogram is one of those kind of things that you might see, looks like this. I have different values along the way, and I say, here's how many happened, and you look and go, oh yeah, I can see what the group is doing. Most people are here, that kind of thing. These are the outcomes. This is the frequency. Last day we talked about a frequency distribution. How many times did a particular outcome occur? That's called its frequency. And then when we graph the visual, we can see exactly what's going on, okay? Okay, somebody have a question? By the way, I don't see chats. I cannot see a chat. I have it on full screen.
Oh, yes. But wouldn't that basically be a bar graph?
That is a great question. It's not exactly the same. Does anybody, well, actually, I wouldn't expect anybody to know the difference. We're just learning this. A bar graph, I'm going to give you, a bar graph would be something like this. This is a terrible picture. I can't draw straight lines. That's a bar graph. A bar graph, I have outcome, 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 and I have space between the outcomes. With a histogram, there's no space between the outcomes. So every possibility is captured. See, there's nothing in here, there's nothing in here, there's nothing in here. So if we were talking about particular outcomes, it doesn't even matter what we're measuring. A histogram, every outcome goes in someplace and every possible outcome is covered. Whereas with a bar graph, only that outcome is covered and then the next outcome, but if there are possible outcomes in between, we just skip them. They're very, very similar in nature, but the bar graph from a mathematical standpoint isn't as useful because the histogram, there's more information that we can gather from it. Plus, there's no calculation that can take place with a bar graph. With the histogram, we can actually calculate averages and different things. So that's why I like the histogram. So here's what we're gonna do. We're gonna do a couple of little experiments today. And we're going to draw histograms as a result. So there's two experiments. And last day I asked you guys if you had the dice, but not very many people did. So I'm going to bring the die, I'm going to roll it, and we're all going to keep track. Now what I'm going to do is I'm going to roll the die several times, and we're going to keep track of the outcomes. And then we're going to draw a histogram that represents our outcomes. So you can see actually the whole process from beginning to end. This is not a calculation, this is a count. So I'm going to roll one die, okay? So what are my possible outcomes? My possible outcomes are 1, 2, 3, 4, 5, 6. Okay? What I want to do is every time I roll a particular one, I just want to do a tally. Okay? That's it. I just want to put a tally, a little slash mark. So I'm going to roll the die and I'm going to holler out what I'm doing. So everybody should be doing exactly this. Have that in front of you. We're going to do all of this together so we all get hopefully the same picture. So I'm going to roll the die. I'm going to call out what I have. 5, 4, 5, 3, 1. So you can hear my die hitting the table here. 4, 5, 4. Seems to like those numbers. 6, 1, 4, 2. There's my 2. 2, 5, 3, 1. I'm doing a couple more. 5, 5, 3. So what do we got so far? That's 8, 12, 14, 14, 19. We'll do one more. 4. Okay, I just rolled the die, I believe 20 times. These are the outcomes I got. Now, this is not rocket science, but you can also tell something about whether a die is fair. Now, we use that term a lot when later on when we're doing probability, a fair die or a fair coin. A fair die is one where the numbers 1 through 6 are equally likely to occur. Imagine if my die were imbalanced. If it was heavier on one side than the other, for example, the heavy side is more likely to land down, which means the opposite side is more likely to be the one that is exposed, okay? If I have a coin that is not a fair coin, again, unequal balance of the weight, I'm more likely to land heads than I am tails or vice versa. So one of the ways you can actually test for a fair die is not to roll it 20 times, but maybe to roll it, 1,000 times and, look at these numbers. Are they radically different or are they all pretty close together? So that's kind of one way of looking at it. So this is our frequency distribution, okay? So what we're going to do is we're going to draw. Now, generally speaking, by the way, I prefer doing this on a sheet of graph paper. I don't have graph paper, I have a board. So if nothing else, when you're doing this on your quiz, use a ruler. So it looks, the straight portions will actually look straight. So my vertical, my horizontal. Now, the outcomes, this is not the XY plane from algebra. It doesn't work that way. This is not 0. 0 is wherever you want 0 to start. Now, my outcomes are the numbers 1, 2, 3, 4, 5, and 6. So I want to place them, maybe I'll put 1 here, and I'll put 2 here. Then I want these equally spaced. These are outcomes, not counts. The vertical is the frequency. How many times did each one occur? Now, the most you see here is 6. So I want these equally spaced. Again, maybe 1, 2, 3, 4, 5, 6. Okay. Every now and then label them so you can see what's going on. Oops. So what I want to do is build my little rectangles. Now, where do I put the rectangle? Do I put the rectangle to the left of the number 1? Do I put the rectangle to the right of the number 1? Neither. I center the rectangle on the number 1 because number 1 is the only outcome. The number 1 happened 3 times. So I'm going to go up to 3, just like this. Everybody got that? The number 1 occurred 3 times. So I draw a rectangle where the number 1 is centered in the rectangle, not the left or right endpoint, because that actually creates a little bit of ambiguity. Now, the number 2 happened 2 times. The number 3 happened 3 times. The number 4 happened 5 times. Again, graph paper is the best way to do this. The number 5 happened 6 times. And the number 6, it only happened 1 time. Okay, so here's a visual representation of my outcomes, and each outcome is centered in the rectangle. So it makes it really simple to interpret. Now, when I'm looking at this picture, I say, yeah, it's kind of heavily loaded. 4 and 5 occurred. 6 doesn't occur very often. You can't really make any conclusion in terms of the fairness of my die, not with just 20 rolls. Now, here's a very important thing. Make sure these numbers match those numbers, and also make sure your total frequency adds up to the number of times that you did it. The number of times I do something is called the number of trials. So I did this 20 times. So there are 20 trials. That sounds like a strange word. It means I tried something 20 times, literally. So this is a histogram. Now, something I want you to notice. For example, the number 3 occurred this many times. Great. But in terms of numerical values, if the 3 is actually in the middle and the 2 is actually in the middle, then what would the value of that number be? Anybody want to try that one? What value would that be? If that's a 2 and that's a 3, anybody?
2.5.
2.5. That seems strange, and that would be 3.5. So the number 3 goes from 2.5 to 3.5. You say, but you can't get 2.5. You're right. That's why we use 2.5. I mentioned this last day. When you're doing this sort of thing, we didn't actually draw the graph last day, but I said when you're choosing your boundaries, the boundaries would be from here to here. You want to use values that are unattainable. That way, every value falls into classification. Here's the danger of not doing that. Could you imagine if I had drawn a histogram and I said, all right, the number 1 happened 3 times, 1, 2, 3. Here's my 1, and 1 happened 3 times. And then the number 2 happened 2 times. And then the number 3 happened 3 times. Now, when I'm making my rectangles, how would I do them? Do I go this way? Or do I go this way? It's kind of ambiguous. And this bar is part of this rectangle, but it's also part of this rectangle. There's definitely confusion if I made the outcome also where I draw the vertical, because then is it on the left? Is it on the right? Nope. My outcomes should always be in the middle, and the border lines, they're called the boundaries, should be halfway between things. Now, I used an analogy last day. I talked about point spreads in sports, like Super Bowl. The reason you always see, or not always, but you often see point spreads of impossible numbers. For example, you might hear, the Rams are favored in the Super Bowl by 3.5 points. And the obvious thing you should be saying to yourself is they can't win by 3.5 points. That's impossible. You're right. So if they win by 3, one group of people win a bet. If they win by 4, a different group of people win the bet. So you pick a point spread that's halfway between possible outcomes. See, that's the best way of doing it. Now, if you said the Rams, we favor the Rams to win by exactly 3, and then if the Rams win by exactly 3, guess what? Actually, nobody wins the bet, because you're saying that's the tie in a sense. It'd be kind of like this. I'm gonna play one-on-one with LeBron James later on today. Okay, I'm gonna play with LeBron. We're gonna play first person to 20 baskets wins. Yes, I know all of you are probably gonna bet on LeBron. Sure. Oh, but what if I said I get to start with 19 baskets? Ooh. So can Mr. Brown make 1 basket before LeBron makes 20? Maybe I get lucky, but I'm starting with 19 baskets. So that means LeBron is favored by 19 baskets because you're going to give me 19 to start. That's what's going to make it even. Now, he either gets to 20 or I get to 1 first. But because I get to start with 19, that's what we're calling a tie, and then we play from there. If in the Super Bowl, the Rams are favored by 3, we're saying, okay, we're going to give the other team 3 points in a sense. Now we're going to play a game from there. If the Rams end up winning by 3, then it's exactly what we said. It's like it's a tie. They got to win by more than 3 or win by less than 3. But what if they win by exactly 3? Well, then nobody wins the bet. Except the casinos. They win the bet, believe it or not. That's how it works. If it's a tie, you don't win, they do. So we choose halfway in between because that way there's no possibility of confusion as to where an outcome would lie. So this is a really simple visual representation. We're going to do another one in a moment. Before I move on, any question about this? Okay, this is called a histogram. Again, no gaps, and every outcome is completely covered. And then the visual is actually really simple, I think, to interpret. Okay, now we're going to do a different example. Now we're going to do coin flips. Coin flip is one we study a lot in statistics because it's just so easy to understand. And there's not really a calculation involved as much as a count. So what I'm going to do now is I have 3 coins in my hand. Okay, I have 3 dimes. And what I'm going to do is I'm going to flip them simultaneously. I have 4 possibilities. I get 0 tails, I get 1 tail, I get 2 tails, or I get 3 tails. Okay, I have 3 coins. Those are my possible outcomes. Now, if I thought that my coins were unfair, unequally weighted, then I would expect to see way more tails or way more heads. But when I flip 3 at once, I might see 0 tails, and then the next time see 3 tails, and the next time see 1 tail, next time see 2 tails. All outcomes are possibilities. So we want to do this several times. We're going to do calculations with this in a few weeks, but we're not ready for that yet. So this is going to be a 3-coin flip. What I'm describing, this is the experiment. This is called an experiment, and now we're going to do a count. Now, how many times should I do this? Well, I want to do like what we did last time, probably maybe 20 times. And so what are my possibilities? My possibilities were 0. Oh, and we're going to, I can't spell. We're going to count tails. Sorry. Okay, so I can get 0, I can get 1, I can get 2, or I can get 3. These are my possibilities. And like before, we're just simply going to do a tally. Okay, so I'm going to do it off to the side here. So first one, I got 3 tails. Wow, on my first try. All right, hold on a second. All right, let's do it again. I'm going to do this several times. Next time I got 1 tail. Next time I got 1 tail. Next time I got 3 tails. Next time I got 1 tail. For whatever reason, we just don't want to get 2, do we? I got 2 tails finally. These are simple experiments you can actually do on your own, obviously. Oops, hold on, one fell off the table, that doesn't count. Try that again. I got 1 tail. I got 0 tails. I got 2 tails. I got 2 tails. I got 3 tails. Wow, look at this. I got 3 tails once again. I'm wondering about these coins. Are they fair coins or are they unfair coins? I got 2 tails again. We don't seem to see a lot of heads in this example here. I got 1 tail. Said we're going to do this 20 times, so we're almost done. I got 1 tail. I got 1 tail. I got 0 tails. Let's see, 9, 17. So 3 more tries. I got 2 tails. I got 1 tail. I got 1 tail. All right. So 10. Oh, 1 more. It doesn't add to 20 yet. And I got 1 tail. Oh, you know what? I just did an extra. That's only 4. Sorry. Try that again. I can't count. It's 11. Okay, there's my 20. Now, what I would like is for everybody here to make their own histogram, just like we did last time. So I am counting. I'm counting the number of tails. My possibilities were 0, 1, 2, or 3. So on my thing, I have 0, I have 1, 2, 3. Yes, 0 is a possible outcome, but we don't put 0 up against the edge. It's too hard to interpret. It's an outcome. Okay. On the vertical should be the frequency. Now, the highest frequency was 9. So maybe that's 2, 4, 6, 8. Okay. 1, 2, 3, 4, 5. We'll put 10 right there. That makes it easy. Yes.
I'm sorry, I have a quick question.
Yes.
Can you explain again how you got the number? I mean, on the side while you're numbering those differently again?
Oh, well, what am I out? Now I'm counting the number of tails in any individual flip. I flipped 3 coins. So the only possibilities are 0, 1, 2, or 3. Do you agree with that?
Yes.
Okay, now how many times did it happen? That's the frequency. That's what the tallies represent. They represent the number of times it occurred. So for example, 0 occurred how many times? Exactly 2 times. So I make that particular block too high. So we're going to do just like we did with the die, except this is slightly different. With the die, my outcomes were the numbers 1 through 6, and I just tallied every time I got a 1 through 6. Now I'm actually counting the number of tails on each individual flip. So that's my possible outcomes. So what we want to see is a visual of that. Does that make sense?
Yes, Professor, thank you.
This is not complicated. This is just basically a visual. And if every one of us did this experiment individually, every one of us should expect to see a different set of outcomes. All right, our coins aren't talking to each other. Oh, I landed 2 tails. You guys gotta land 2 tails now also. So let's everyone try this on their own. This is what you're starting with. And see what that ends up looking like. Okay, just let me know when you're done. Just say, I'm done.
Done.
Okay, I want a couple people to be done before we actually see. We'll all agree then. So we should have exactly 4 rectangles because there were only 4 possible. Right? I could do the experiment 1,000 times, but I still only have these 4 possible outcomes because I flipped 3 coins. I can't get 4 tails. I can't get negative tails. I certainly can't get 2.5 tails. So I'm going to get 0, 1, 2, or 3 every time. So hopefully then you got something that looks like this. There's my 2. Now that's 9. And graph paper makes this really easy. You don't have to estimate. The number 2 happened 5 times. And the number 3 happened 4 times. So hopefully we have a picture that looks something like this. Now, what's interesting about coins, and again, this is called probability. We're going to get to this later. What do you think is the least likely outcomes? Anybody want to try that one? I'm going to flip the coin 3 times. What's the least likely outcome, or what are the least likely outcomes?
0 and 3.
Excellent. To get all 3 be the same is the least likely. You say, well, why is that? Because to get 1 tail, there's 3 different coins I could get 1 tail. There's 3 different ways, in other words, I could get 1 tail. There's 3 different ways I could get 2 tails. That means I can get 1 head, but there's only 1 way I can get all 3 to be tails, and that's all 3 be tails. Think of it as first coin, second coin, third coin, right? The tail could be the first coin or the second coin or the third coin if I got 1. So the least likely would be the extremes. These are the most likely. Now, my coin didn't know that, but even in my picture, those ended up being the highest rectangles. Those ended up being the shortest. If I did this enough times, what I'd probably see is the middle group being higher and the outer groups being lower. And we're going to actually do this as a calculation in a couple of weeks when we get to probability. It's actually not that far off. In fact, let me tell you, I have a syllabus right here. Actually, somewhere I have it. Where is mine? Nope. Well, I had it last night and seem to have monkeyed around with it. Oh, here we go. Here we go. We start the concept of probability actually next week. I said a couple of weeks. 1 week away, we start probability. Probability is my favorite part of statistics. It's the part to me that actually makes the most sense because I can physically see the outcomes. For example, we just flipped a coin. We can see the outcomes. But in the terms of probability, most of the outcomes are what we call theoretical. I'm telling you we're equally likely to land heads or tails. So therefore, if I do something a whole bunch of times, what are my likely results? Now, when we say likely results, that's not a guarantee. Okay, that's certainly not a guarantee to win or lose. Are there any football fans here? Anybody here a football fan? Just even casually? Just say if you are.
I was.
Yeah.
You was.
Yeah.
One of the things I find very interesting, I'm a big football fan. I love football. And a lot of times I will turn it on my computer because the game I want to watch isn't on television, let's say. So I'll go to my computer, I'll go to something called Gamecast, and it'll give you kind of a play-by-play of what's happening. But what is very interesting, there'll be a section where it will say the probability of that team winning. And it might be at halftime, the probability is 53.8%. How do they know? They still got to play a second half, but because one team's ahead, and as the game goes on further and further, now you're in the fourth quarter and one team's up by maybe 14 points. Now it might say the probability is 96% they're going to win. And now we're down to the last play of the game. It might say the probability is 99.8%. It will never say, by the way, at any point during the game, it'll never say it's 100% that one team's going to win, because that means it's an absolute certainty that one team's going to win before the game is finished. And anybody who's ever watched football long enough knows that crazy things can happen. The same thing is true if you watch basketball. The same thing is true if you watch hockey. It will actually give you percentages along the way of one team winning based on just simply probability of things. What is the likelihood of things? And that sounds crazy, but it's true. So if you were a card player, okay, maybe you like to play poker, maybe you like to play different games of, and you're looking at the cards in your hand, it's actually possible to calculate what is the likelihood or the probability that you will win based on what you have. Now, does that mean you will win? No. Does that mean you will lose? No. It's just the likelihood. So before I flip this coin, what is the likelihood it's going to land tails? Anybody want to try that one?
50-50.
Yeah, we say 50 days, 50% likely to land tails, or 1/2 the time. That's a perfect answer. Now, when I flip the coin and it lands tails, does that mean it's always going to land tails? No, because when I do it the next time, it starts over. The coin doesn't remember. It doesn't know what it just did. It's going to start over each time. And that's one of the funnest parts about probability, is that it always starts over. Now, I want to do one more example of a histogram, and now we want to do it with actual outcomes that look slightly different. So if I had, let's say, I could give let's say I give a test, a large group of people took a test. And the thing is, that means I've got lots and lots of outcomes. I might not see the same outcomes, but I might see clusters. In other words, you might say, well, here's all the people that got A's, here's all the people that got B's, things of that nature. Or you might just say, here's the outcomes, in a certain range, here's an outcomes in the next range, and so on. The thing is, between ranges of outcomes, we don't want gaps. We don't want gaps. So we would always say, from there to there, we say, for example, in a classroom, we say from 90 to 100 is an A, and now from 80 to everything up to 90 is a B. That's a really simple way of thinking about it. That would be a histogram. If I was talking about test scores, might be the same thing. If 50 put you in one category and 49 put you in the next category, then we might need 49.5 then to be the line in the sand. Everything above is in one group, everything below is in the other group. So that's usually what we do with the histogram, is that we take the halfway in between, the unattainable value, and make that where we put that vertical bar. That way you're always on one side or on the other, like we just did with the coin flips, like we just did with the roll of the die. Okay, this is not complicated. It's purely for the visual effect. That's it. Now we're going to talk about central tendency. This is a new thing. And again, central tendency. Well, tendency. There we go. Anybody, when you hear central, what connotation? What comes to mind when you see the word central? Central.
Average.
Well, even kind of average is good. How about like middle? Does that make sense? Like, central in the United States, we talk about the central time zone or something. We think kind of like in the middle of the country. Central tendency is a form of average. Excuse me. We think of it kind of like the middle. Tendency is what is likely. Sorry, I need to drink something. So central tendency is, think of it this way. I have a large group of numbers. And don't think small, think big. Think big thoughts. I have a large group of numbers. Can I use one value to describe a large group of numbers? Now that can be very dangerous, trying to use one value to describe a large group, but if I could only use one value to describe a large group of numbers, the word average is probably the best choice, okay? So let's keep it simple. If we were talking about employees at a particular company, maybe I want to know what is the average number of years they worked for the company. Maybe I want to know what is the average salary that somebody at the company has. Maybe I want to know what is the average age of the employees of the company. I only have one number to describe maybe a large group of employees. I wouldn't want to describe my group of employees by taking the oldest person or the person who makes the most money or the person who's been there the longest to describe the entire population of the company. That would be less, less helpful, less useful. I want to describe a group of people's average height. I'm not going to use the tallest person in the group any more than I would use the shortest person in the group. I'd probably want to find somebody in the middle of the group. So there's three common forms, and I'm going to talk about all of them. The mean, the median, and the mode. There are others. Those are what we call the big three. Now, let's suppose you individually, let's keep it really simple. In a particular class, you got 70 on the first exam, you got 80 on the second exam, and you got 90 on the third exam. And you would tell people, well, you know what? On my three exams, my average was 80. Does that sound like an accurate description there? My average was 80. What do you think? 70, 80, 90. Do we agree that the average would be 80? Even if we don't even know what that means, you'd say, that's how I was doing in that class. I individually, I don't say my best score was, or I don't say my worst score was, because that doesn't tell me the rest. I'd say that was my average. That's kind of the middle for me. So the mean is always a numerical measure of all of the numbers involved, but it's one number. So how do we calculate the mean? Now I'm going to introduce some notation. People don't always like notation. So I kind of have to do that because it's a formula. So if I say my scores, okay? So let's say we have n values. N is however many. N could be 2, n could be 2,000. I have this many values, that's it. What are my values? Well, typically in a notation sense, we write it like follows. My values are x1, x2, x3, on and on until I get to xn. So if I have 10 values, that just means the first value, the second value, the third value, the 10th value. Okay, the subscript just says what order was the first score, second score, third score. It's not the highest score, lowest score. No. It's just I'm looking at a bunch of numbers, and we usually describe it that way. So to find the mean, the first thing I need to do is add all these up. Now there's a symbol mathematically that we use for adding up a bunch of numbers. Does anybody know what symbol we use that indicates you're adding a bunch of numbers? I'm just curious. It's this symbol here. This is a capital sigma. It's a Greek letter. Whenever you see this symbol, it always means you're going to add up a bunch of numbers. This is true in every math course you'll ever take, that if you see a sigma, sigma always means sum. I'm going to add up a bunch of numbers. And a lot of people think, oh gosh, this is evil notation. You know, that person who was always picked last for kickball, it was their idea, right? They're getting back at us. Actually, I love this because it's a shortcut. Let's say I had 1,000 numbers and I want to add all of them up. That would take a long time to write down my intent. Instead, we write it this way. I want the sum of the x's. These are my scores. This just says the sum of the scores. That's it. Oh, so what this means literally is x1 plus x2 plus all the way down to x plus xn. I want to add up all the numbers. So we just put a summation in front of the x. That's it. Oh, but that makes it really convenient. So now we're going to define the mean. Okay, there's two possibilities. I could have a population, I could have a sample, and we always want to distinguish which one it is, because most of the time, by the way, the vast majority of the time, you're going to be working with samples because you may not have the ability to find the population, but sometimes you might have the population. You see, we might be doing a problem where the population is just the people in our class. We want to know, for example, the average age of the people in our class, or the average height of the people in our class, or the average income, or the average number of units they're carrying. And that's our population. Then is it reasonable we'll have every single value? Yeah, it's totally reasonable. Okay, in fact, it's what we would always start with. So when I want to find the mean, there's two. The population, we use the Greek letter mu. Mu looks like kind of like an M with a tail, mu. Some of you have heard it, and it's spelled MU, and it's what a cat says. A lot of you don't realize your cat, it speaks Greek, yeah, because isn't that what cats say, mew? Mew, mew, anyway, I know, bad joke. Mu is what we use for the population. For the sample, we use a different symbol. We use X with a bar over it. And we actually say X bar. So we say mu, we say X bar. Both of these mean the exact same thing. They mean the mean. One's the mean of the population, one's the mean of the sample. You would always know ahead of time which one you're dealing with. So if I said, we're going to talk about census data. Okay, remember what the census is. That's a measure of every single person in the entire country. So any form of average I use when it's the census would be a population average, because I have every single person in the entire United States. So if I'm dealing with the census, then I would be dealing with a mu. If I just said, we're going to talk about, random people across the country, when we want to measure people about something, maybe I grab 1,000 people from around the country and I measure something about them. That would be a sample mean. Okay, X bar, because I didn't do everybody, I did a sampling. So the formula is actually very, very simple. Down. Okay, there are N in the population. There's little n in the sample. Little n refers to how many values there are in the sample. Capital N refers to how many values there are in the population. And the only reason we distinguish it, it's still N. N stands for number of people or number of things. We distinguish it to remind ourselves, oh, population, sample. Mu is equal to the sum of all of the values in the entire population over the number of things in the population that I'm measuring. X bar equals the sum of all of the things I'm measuring over the entire size of the sample. You notice the formulas are exactly the same. In both cases, I add up all the values and then I divide by the number of things that I'm dealing with. The difference is this is a sample, so that's not the whole population. This is the whole population, but I calculate them the exact same way. Add up all the values, divide by the number of things. I don't say the number of people because I might be talking about, number of dogs or, number of made baskets at a basketball game or something like that. So let's do a simple example. And by the way, most of the time we'll be dealing with this. So let's suppose I want to find the mean of a sample with values, let's say 3, 5, 10, 12, 16, 18, 21, 24, 30, 36, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I want to find the mean of a sample with these values. These could represent whatever you want them to represent. I have a sample and these are the values that I have. I want to find the mean of the sample. So the first thing we have to do, we got to add up the numbers. So you can do this in your head. It's more practical to use a calculator. So what is the sum of all my values? Well, let's do it. So 3 plus 5 plus 10 plus 12 plus 16 plus 18 plus 21 plus 24 plus 30 plus 36. When I added all these up, I got 175. Now, an absolute rule in statistics, always do it 2 times. You say, well, I have really powerful technology. I'm doing this on a computer. Great. Do you know why you always do it 2 times? Anybody? Try this. Why do you always do this twice? When I say add up the numbers or do any calculation twice?
Make sure your math is,
I'm sorry, start, Lila, you tell me first. Why
make
always
sure
do
that your math is perfectly done.
Okay, Robert, why do it twice? Will you say the same thing?
Human error.
Human error. By the way, one of my favorite excuses that people use is, oh, it's a computer error, or it's a calculator error. No, your calculator doesn't make an error. Your calculator gives you the answer of what you input. It's the input that I might make a mistake. Have you ever, when you were typing on a keyboard, spelled a word wrong because you hit the wrong? Of course you do. Everybody does that. Have you ever entered a number incorrectly on your calculator? Of course, everybody has. When I just enter those numbers, it doesn't matter if I have the most powerful computer on planet Earth. The computer's going to give me the answer to what I entered. But if I don't enter it correctly, it's going to give me an answer to a different question. That's not a computer error. That's called a user error. It's an input error. I always recommend that you do everything twice. And then if you get the same answer, you can trust it. You say, okay, I entered everything correctly. But what most of us find, this is the worst thing. I did it, I got an answer. I did it again, I got a different answer. So now what should I do? Probably do it a 3rd time and pray that you got one of the first 2 answers, that you don't have a 3rd answer. If you're getting a different answer every time, stop, slow down. You're being careless in your entry. But by the way, sometimes we have lousy calculators that the buttons may stick. Or like me, you got fat thumbs. So when I text people, I misspell half the words because my thumb is on a different letter half the time. So always do it twice just to be absolutely certain that that's correct. Okay, so that was easy enough. So is my answer 175? No, 175 is the numerator of my answer. What's the answer? I'll use a different color. The answer is X bar equals 175. Help me out here. 175 over what?
10.
10. That's the answer. Now, if you can reduce that, reduce that. If that's a terminating decimal, which it is, then write out the terminating decimal. This is exactly 17.5. That's a perfect answer. So the mean of these numbers, and when we think mean, we're thinking numerical average, okay? Is a mean always the best? We'll discuss that. Maybe it may not be, we don't know. But the mean is literally, I added them all up, I divided by 10. So this might be, you're a basketball player. Keep it real simple. You're a basketball player, you played 10 games. And here's how many points you scored in each of those games. So what would 17.5 represent? That would be your scoring average. You average scoring 17.5 points per game. It's actually that simple. That's what it would mean. Do I put any weight or any value on that? No, that just means that's what I do. Maybe these are quiz scores and that's my average quiz score. So when we say average, most people, when they use the word average, they probably mean mean. Okay, they probably, that was their intent. It isn't always the case, but it's probably the case. So finding the mean of a group of scores is actually quite simple. It's just add up all the scores and divide by the number. Now, that worked because all my scores were different. Here's an example I like to use. All right, I am a professor at UCSD, okay? And I have a typical class, I might have 400 people in the class. So what I did today was I gave a 5-point quiz. I gave a 5-point quiz to those 400 people in the class. And I'd like to find, how did they do as a whole? What was the average? So on my 5-point quiz, What were the possible scores? Well, you could get a 0, a 1, a 2, a 3, a 4, or a 5. So on my 5-point quiz, here's what happened. I had 6 people get a 0. I had 31 people get a 1. I had 74 people get a 2. I had 111 people get a 3. I had, let's say, 187 people get a 4. I need a calculator here. Hold on. 6 plus 31 plus. And I had 91 people get a 5. Okay, had to make sure they added up to 400. I gave a 5-point quiz to my class at UCSD, and here's the frequency distribution. This is why this is so useful. I could make a histogram. It would be really easy. And my values along the horizontal would be 0, 1, 2, 3, 4, or 5. My values along the vertical would be these frequencies, with that being the highest frequency. So now the question is, I would like to know the class average. What was the mean? So what does that mean? Well, if I wrote down all the scores, by the way, here's what I'd be writing down. And by the way, it's okay to have them in order. That might make it easier. So I would have the following. I'd have 0, 0, 0, 0, 0, 0, 1, 1, 1. Do you think it's practical for me to write out all 400 scores in order to do this calculation? Do you think that's a good idea?
No.
I think it's probably a terrible idea. And if you said terrible idea, you're right. Not only would that take me a really long time, now I want to find the mean. So I'm going to go 0 plus 0 plus 0 plus 0 plus 0 plus 1 plus 1 plus 1 plus 1. What do you think?
No.
I need to find the sum of all the values. I can't answer this question without finding the sum. By the way, you don't simply say 0 plus 1 plus 2 and so on, because the score of 3 happened 111 times. So in this example here, if I want the sum of my scores, how many times did the score of 0 occur? It occurred 6 times. How many times did the score of 1 occur? 31 times. That's equivalent for me saying 1 plus 1 plus 1 plus 1, 31 times. How about the score of 2? How many times did it occur? 74. You see what I'm doing here? Is that the equivalent? Is this exactly the same as if I wrote 2 plus 2 plus 2 74 times? Do you agree that's exactly the same thing?
Yes.
A little more efficient though. This might not take me nearly as long. Okay, now what? Keep going. What should I put next?
111, 3 times.
111. I had the number 3 111 times. Aha. You guys have figured it out. Now, when I do this, will this be the sum of all 400 scores when I do this? What do you think? Yes or no? When I add up these numbers, it'll be exactly the same as if I had all 400 scores and I added those up. Do you agree?
Yes.
Yeah, little more efficient. Yeah, a little bit more efficient. I don't need to say 5 plus 5 91 times. How about just 91 5s and 187 4s and so on. Now let's add these numbers up. Okay, so 0 plus 31 plus 74 times 2 plus 111 times 3 plus 187 times 4 plus 91 times 5. Everyone should be trying this and tell me what you get in the end. Okay, tell me when you got a number. And I'm going to do it a second time just to be safe.
I got 4. Oh wait, you know what? I think I forgot the 6.
Anybody got a number? We all want it, hopefully we all get the same number. That would be a good thing.
I got 501.
501
Yeah.
should be a little bit bigger than that. Did you finish the second row? Because that's over 400 right there. That's over 700 right there. This is why we always do it 2 times. I did it 2 times, by the way, just so you guys know. I did it twice. I don't say that jokingly. I actually do everything twice, and I got the same number, which makes me more confident. Anybody? Again, you please use a calculator for this. Oh, you know what? I just realized. I just realized I said 400 before, didn't I? There's not four. There's actually
Yeah, it's
500.
500.
There's five. There's sorry. My end is 500. We haven't finished up. That's funny. Okay, that just means that's going to be ultimately be my denominator, by the way. So, does anybody have a sum?
1715.
That's what I got. I got 1715. Did you do it 2 times?
No, I only did it once.
Oh, you have such tremendous faith. I don't have faith in myself.
I put in numbers really slowly.
Oh, okay, okay.
So.
The thing is, you're basically going 6 times 0 plus, 31 times 1 plus. You're doing this all the way to and hit equals, and hopefully that's what you got. Question, somebody?
Yeah, just a quick question, because I keep getting like the first time I said I got a pretty small one. The second one I got a huge number, different from the answer that I got.
You may be hitting the product the times too many times.
So
now,
how would you put that in said calculator?
Well, here's okay. Let me hold on a second. Put the pen away for a second. Okay, let me just do the first few and I'll hold it up to the screen. So what I'm doing, I go 6 times 0 plus. One thing I like about these calculators is I can see a readout of what I actually entered plus. 31 times 1 plus, I'll do one more, 74 times 2. Now, hopefully you see on my calculator, it's telling me exactly what I just entered. And I'm keep going, plus 111 times 3 plus 187 times 4 plus 91 times 5. Okay. It's giving me a readout. So if I do hit a misentry, I can actually see it. And then I'm just hitting equals in the end. So if you're slow, I like what Destiny says, just do it slowly. You're using a calculator. That's already going to speed things up tremendously. But entering 6 times 0 plus. Now all of us will make the mistake of hitting the times when we mean a plus and hitting the plus when we mean a times. That will happen occasionally. But if I have a calculator, any calculator that you can see what you entered. Graphing calculators are wonderful for that, but this is a cheap calculator that shows me a display of what I've entered. Then if I hit a wrong button, I can see it on the screen and then I can fix it. That's about all you can do. It doesn't matter what technology you have, like I said before, if you misenter the values. So what does this mean? This means our class average is 1715. Are we done?
No.
No, you have to divide it by 500.
That's my numerator. That's the total of if every single person in the class, we just threw all of their points in a pile. If you got 5 points, I'm going to give you 5 tokens. If you got 3 points, I'm going to give you 3 tokens. How's that? And then at the end, everybody throws all their tokens in the middle. That's how many tokens we'd have. So my mean, which in this case would be X bar, because I don't think this is a population of planet Earth or something, is 1715 over 500, which is exactly what? Anybody?
3.43.
3.43. Now, looking at those scores, do you think that's reasonable? My average was a little better than 3. You'd say, yeah, more than half the scores were 4s and 5s. That seems reasonable. That seems reasonable. That's actually an answer that would make sense. Can you tell me a bad answer? So in other words, I think I did everything right. I think I'm doing everything correctly. Let's suppose I said, well, I only have 6 possible scores, so let me divide this by 6. Bad move, obviously. Do you agree? Dividing by 6? There's 500 people, but I only have 6 scores. No. There's 500 people. If I divide by 6, tell me how that I would know that's a terrible answer. And it is a terrible answer. 1715, and I divided by 6 rather than 500. Tell me why I know this is a terrible answer. What's my answer? My answer is 285 and 5.6. On a 5-point quiz, the average was 285. You think that's probably a terrible answer? Yeah, that's a terrible answer. On a 5-point quiz, shouldn't my average be somewhere between 0 and 5? So I said, how do you know a bad answer? Well, you have an answer that's not possible. I have a 5-point quiz. The average has to be somewhere between 0 and 5. What if everybody in the class got a 0? Well, then my average is 0. If everybody got a 5, the average is 5. And in actuality, the average should be somewhere in between. If my average isn't between 0 and 5, then it can't be a very good answer. And every now and then we will hit a wrong button and we'll get an impossible answer. And that's how I know. So the mean is one of the simpler concepts. Just add them up, divide by the number. That's it. You know, it's not that exciting, but it is. Okay, that's what it is. Any question on this before we continue? It's a fairly simple notion. Now, I want to take a short break because we've already been at this for over an hour. We have a few more things to go over, but the mean is probably the most common form of average, and it's the one that most of us probably have the most comfort with. We say, yeah, I'm used to this. You know, if someone said, you know, take all of your siblings. Now, how many children do they have? What's the average number of kids all your siblings have? You know, it's easy. Add them up, divide by the number. And things like that, fairly simple. If I said over the last 10 years, what was your average income? Well, go back to your tax return and say, how much money did I make the last 10 years each year? Add them up, divide by 10. That's such a common thing. It's only simple if you have a calculator, but it should be simple. Right? There's nothing about that should be disturbing. So I'm going to stop here. We're going to take a break because we still have a few more things to go over in terms of forms. This being probably the most important, certainly not the only one. So I'm going to pause for a bit. Boom. Now, the mean is a very important value, and it's something we use in most calculations. But is it always the best? Is it always the most accurate? Now, I have some fun with this one. Okay. Because let's suppose I said, all right, I'd like everybody on a piece of paper, I want you to write down last year's income. Okay, I want you to write down last year's income, and we're going to find out what is the mean income. What's the average income of the people in our class? And so everybody writes down their income. And by the way, I don't want any names attached. And I collect these pieces of paper and then I add them up and I divide by the number of people in the class. And I come out with, oh, wow, we have a group of people and last year's income for our class was $246,873. This was the average income last year for our class. And some of you would be saying, I didn't make that much money. And someone might say, I didn't even work last year. And our average income for the group, and I checked it 5 times. I double checked the calculations. And you'd say, how is that possible? Oh, that's because last year, you guys don't know, Robert was investing in Bitcoin last year. And Robert, let's say, made, 4.2 million. Okay. He's going to take us all out to lunch later. You see, when I added up all the numbers and divided by the number of people, we had one really, really large value. Do you think this is an accurate reflection of the group's income? Well, if there's 15 people in the class and 14 people made significantly less than this, this might be the mean, but is it the best measure of the average income? Now think about that for a moment. What do you guys think? Is that the best measure of the average income if everybody in the class but one is below it?
No.
Probably not. This is one of these things that a lot of folks don't understand. When we use the term average, I always laugh when, I'll have instructors tell their class, we just had a test. Everybody was above average. That's really not possible. In fact, generally about half the people should be above average and about half the people should be below average, if you kind of think about it. You see, if I gave a test to our class, everybody can't be above average because that wouldn't be the average. The average should be kind of in the middle. So the problem here with income, you can make $0. But we talked about this last week. Is there a highest income? Technically, no. No matter how much money somebody makes, somebody could always make more. So we say it's open-ended, it's unbounded. Therefore, the mean is a very dangerous measure. You see, it doesn't take very many Bill Gateses to make the average income look artificially high. You see, you have one really, really, really wealthy person, it makes the average income look much higher than it actually is. So maybe the average income might not be the best. So there's another measure that, particularly when things are open-ended, income is open-ended. There's no highest, even though there's a zero. And this is called the median. Now, median. Does anybody know what median literally translates to? We have a period of human history roughly from about 500 to 1500 AD. It's called the medieval period of history. What's another name for that? Anybody? The medieval period of history is also called, there's a more common term. Anybody?
The Dark Age.
Well, the second part, right. Not the Dark Ages, but the Dark Age was part of that. The Middle Ages. The Middle Age was that period called the medieval period of history, is also called the Middle Ages. Yes, there were some dark periods during the Middle Ages. The Middle Ages, often called the medieval, that's M-E-D, median literally translates middle. Not numerical average, just simply middle. Oh, okay. So if I have a group of anything, could be numbers, could be sheep, could be people, whatever. I have a bunch of things and I put them in order. This is absolutely critical. They have to be in order, either ascending order getting bigger or descending order getting smaller. But I have a group of things, we're going to use numbers to make it easy. I have a group of things that are put in order. Median quite literally translates as the middle. Okay, so let's suppose I have the following numbers. I have 1, 3, 9, 15, 18, 27, 30. Is there a middlemost value? Is there a number that is smack dab in the middle of this? Anybody? What do you think?
15.
15. That makes it really easy because there was an odd number. There were 7 values, so there's definitely a middle. There were exactly 3 values on one side, 3 values on the other. So 15 would be the median. By the way, is 15 the mean? Probably not. If I added up all these numbers and I divided by 7, I don't think we're going to get 15, but that's not important. 15 is the middlemost number, so it's called the median. That's it. Oh, okay. So if I have all my numbers in order, the middlemost number. Now, what if I have a lot of numbers? It might be difficult. 1, 2, 3, 4. That might not be totally practical. You see, I want to go back to this example. Oh, okay. I got 500 values and I want to put them in order from smallest to largest or largest to smallest. How would I do that? Well, if I have an odd number of values, there is a middlemost number. Do you all agree with that? There's absolutely one in the middle if there's an odd number. If I have 3 numbers, it's the second number. If I have 5 numbers, it's the third number. If I have 7 numbers, it's the fourth number, and so on and so on. But won't I have an even number of values probably half the time? Yeah. So what if? Let me change the problem slightly. I'm going to give you one additional value. Oh, well, that makes it kind of tricky. I have 4 numbers. I have 4 numbers. So let me do right there. There's my cutoff. Exactly half the numbers are to the left. Exactly half the numbers are to the right. What would the median be? And without me even telling you, think of it's almost a common sense response here. What do you think the median should involve? Anybody?
The 15 and 18.
So but it can only be one value. So what value should I use? And I definitely want to use 15 and 18. In other words, use the average of 15 and 18, which would be in this case 16.5. My median would be the middle of those 2 numbers, the average of those 2 numbers. So the median for this group of scores would be 16.5 because it's right in the middle. Now, another way of thinking of median, kind of loosely, if I have a large group of numbers, I'm not talking about I have 5 numbers, I have 5,000 numbers, I have 5 million numbers. Is there a number where basically half the values are on one side and half the values are on the other? If there is such a number, then that is what the median is. The median is the middlemost number. So again, the idea that I'm sort of splitting my numbers in half. If there's an odd number of values, there is an exact value, half, basically half. If there's an even number of values, then what I do is I find the 2 middlemost values and I just go halfway between those. That's it. That's how median is found. It's either an odd number or it's an even number of values. Even number, I do this. Odd number, I pick the specific value. That's it. That's kind of simple. So I have all of these values here. I have 500 values up there. Because these are ranked, whether it's lowest to highest or highest to lowest doesn't really matter. I have 500 values. Where is the median? The median would be, I would use the 250th and 251st values because I have 500 numbers. If I put them in order, I don't have one number in the middle. I have 2, the 250th and 251st values. Does everybody see that? Does that make sense? So the question is, if I rank these, what is the 250th and 251st values? Well, that's actually pretty simple. Just look here. How many values are in these 2 groups together? If I add 187 plus 91, what's 187 plus 91? That would be what? 278. There are 278 scores here. So think of it this way. Highest score is a 5. The second highest score is a 5. The third highest score is a 5. The first 91 scores are 5s. Then the next 187 scores are 4s. So the 250th and 251st highest scores are both 4s, aren't they? So what is the median of this group of scores? It's going to be the number 4, because if I put them in order, the 250th and 251st scores are both 4s. So that makes my median a 4. The median, again, is the middle. It's not a calculated value other than doing this, but it's the middle. So why is the median useful? Well, there are 2 areas in your everyday life. If you were watching the news and you were listening to a report, they use these areas all the time. You'll hear things like the average income in the United States last year, and they'll throw a number at you. Are they throwing the mean at you? No. Why? Because of the Bill Gateses of the world, who, right, we have billionaires in this country. If we include their income and then we find the numerical average, that number is going to be way more than most people ever make. Way more, because they're such extreme high values. So when things like income are reported, they always say, if you watch the news and pay attention, they'll say the median income last year was this, the middlemost income. There's another area where we always use median, and that is housing costs. You see, I can have houses be cheap. Is there a cheapest housing cost? Does anybody know? What is the cheapest a house could possibly sell for? There actually is a value.
Is it 300,000?
$1. Sorry, what? I want, for example, I want to give a house to somebody. But I have to do it in terms of a sale. I can sell a house for $1. It sounds crazy. I can sell you a house for $1. You're never going to have a $1 house, but you could sell a house for $1, not $0. But is there a highest value a house could have? No, because no matter how expensive a house is, there could always be one more expensive. So housing costs and income, we say, are open-ended. There is no highest number. There is no highest number that can keep going. So the problem with taking a numerical average, a mean, when there's no highest numbers, is if we include all those houses in La Jolla and Rancho Santa Fe and places like that, these bazillion-dollar houses, that makes the average house in San Diego much higher than most of the houses actually are selling for. So with income and housing, we always use the middlemost number. Okay, now I'm going to give you a simple visual of that. So I want that to make sense to you. So let's say this is the United States, this is our income last year. This would be the frequency, this would be the income. And I think most of us would agree the average income should probably, if this is income, picture-wise, it'd probably be somewhere around here. But this represents the extremely rich because there's no end to it. It could keep going, keep going. When I use all of these values here, what that's going to do is move the mean way over. So if I said the mean income in the United States, it would probably be a number that 90% of the people in the United States made less money than that. And how can it be an average if 90% of the people are below it? You see, you can't say most people are above average or most people are below average. It should be about half the people are above average and about half the people should be below average. Otherwise, it's not a very good number to use for average. So income looks like this. This is what is called skewed. If something is leaning this way, it's skewed. Income, housing look like this. The bulk of the people are here, but then I have the possibility for extreme in the other direction. That's why median is always a better number to represent if the data is skewed, if it's leaning heavily in one direction, okay? So the middlemost score is far more useful in that case. Let me keep going. Okay, is there another situation that we often see skewed? Believe it or not, there's one that in your everyday lives as students. What is the universal average grade in a class? Keep it simple. What's the universal average grade? If somebody is this, we say they're average in school. What grade?
A C.
C. And what score is kind of the universal average C? Kind of 75%. Do we all agree that's kind of most of our interpretation? The universal average score is a C, and the universal average C is probably about 75%. Okay, great. So when a test is given, don't we expect the average typically to be probably around 75%? Now, you could have a really, really strong group of people. I have in my calculus 3, for example, I rarely give a test where the average is below 90% because those folks, if they've made it that far, they're pretty darn good. But I have classes like that. It's not unusual that most of the scores are really, really high, but we kind of think the universal average is 75%. So if I give a test, you know, we kind of would expect something like this. Does that seem reasonable? That I would kind of expect something like that. If 100 is the highest score, then I can't go past 100. But is 50 the lowest score, or is it possible to go lower than 50? Somebody didn't even show up for the test. What are they going to get? A bagel. Wouldn't it really be like this? Isn't that more likely? Isn't it possible to have scores below 50? Of course.
Yes.
Oh, if we're expecting the bulk of the people to be here, it's possible to be down here. This is also skewed, isn't it? Oh, so if I was reporting the average, and let's say most of the scores are in this range, and there's some a little higher, some a little lower, but maybe there was 1 or 2 no-shows. They got zeros. What's that going to do to the mean? It's going to pull the mean this way, isn't it? The mean might not be the best number for an average for an exam. Why? Because the mean of the exam might be below most of the people in the class. That's when you can say, hey, everybody scored above average. Well, no, that's because you had 1 or 2 scores pulling the mean to the left, just like the Bill Gates of the world pulled the average income to the right. A low score could pull the mean to the left. And again, that would mean it's a little bit artificial. I can't give a test and have most of the people be above average, because that means that average isn't an average. The average should be about where the middle was. So in test scores, because we tend to skew this way, income and housing, we tend to skew that way. We usually give the mean, the middlemost score. Because if you give the middle, then a high and a low can't really affect it. It's just, where do the bulk of the people lie? Where's the score where half are above and half are below? Because again, conceptually, that's a more meaningful, right? A more meaningful number. I remember I had stats when I was in college, and the instructor had this great picture. It was like a youth basketball team. And the coach, he's filling it out, all of his players. He had, all of his players were in the 4 foot tall range, 4'2", 4'5", because they were kids. But then he had the one kid who, grew. So he had the one kid who's like 6'2". So he was asking his assistants, should I report the mean score or the median for my height? Because if he reports the mean, it makes his team look really tall because he has one really tall player. But if he reports the median, it makes his team look really short because it didn't include that really tall player in terms of the calculation. It's just kind of a funny idea. It's like, which one should I report? Well, you only had 5 kids, so it's, kind of a tricky one. So the median is the middle, okay? So let's do a simple example of finding a median again. So I've got a few scores, and again, having them ranked is critical. So I've got 0, 3, 4, 8, 8, 8, 12, 13, 16, 16. Okay, what is the median score here? We'll just blur it out if you can see it. What is the median score? What is the middlemost value? Well, I have 10 values. So I have 1, 2, 3, 4, 5.
Wouldn't it be 8?
It would be 8. You could say it's the average of 8 and 8, and you would be absolutely correct. Oh, well, that was easy. Can the score occur more than once? Yep. If I'm ranking my scores, 8 and 8 were the 2 most middle. Now, I'm going to change one thing about this. I'm going to make that 8 into a 10. Now, what's the median score?
9.
9, because I'm still only considering these 2. Did everybody got that? That's it. That's how simple the calculation for median is. Now I'm going to introduce some other terms that you have heard, but you may not have realized what it applied to. Okay, I'm guessing most of you in your lifetime have taken some standardized test. It might be an SAT, it might be an ACT, it might be one of the, in high school, typically. Just say it loudly if you've taken an SAT or an ACT, one of these kind of standardized tests in high school. Just yell it out if you have. Anybody? Anybody ever take the SATs? Yeah, a lot of people do, because those are used when you're applying for college a lot of times. Just that, your GPA, all these things. Okay, so what you got numbers. I'm not even interested in the numbers. Maybe when you were little kids, my kids, when they would go through every year, they would do in April, May, they would do all this testing. And it was this cumulative comprehensive test where they would test their English, their writing, their reading, their math skills. There were many different types. There was the Stanford test. And it wasn't the score they would give. They would say, oh, your child is in the 90th percentile. Have you guys ever heard terms like that? Somebody's in the 70th percentile or the 90th percentile. Does anyone here have children? Does anyone here have kids? Anybody?
Adult.
But you have, okay, I've got enough to share if you guys don't have any. Okay, so Rosalind, when your kids were little and you took them to the pediatrician, maybe even when they were born, they weighed them, they measured their length and all that. Did they tell you things like, oh, your child's weight is in the 40th percentile or their height is in the 7th? Does that mean they scored 40% on the weight test? I mean, think about that for a moment. When they say your kid is in the 40th percentile, what does that mean? Everybody understand what I'm saying? This is stuff we use in everyday language and people go, oh, that's great. What the heck does that even mean? Percentiles are related to this. To be in the 50th percentile is the median. Because percentile means you are higher than that percentage. Oh, so if I'm in the 50th percentile, I'm higher than 50% of the values. But what's the mean? That's the one in the middle. So there's 50% on one side, 50% on the other. 50th percentile is the mean. So if you're in the 90th percentile, that means you're above 90% of all the other values. So if you had a child who was really tall they're 3 years old, but they're already really tall for a 3-year-old. They might be in the 90th percentile, meaning they are taller than 90% of all other three-year-olds. Doesn't mean they scored 90% on a height test. that's not what it means. So on your SATs, you took the English or you took the math and it says you scored in the whatever percentile. That doesn't mean you got that percent on the test. It means you scored better than that percentage of the people that took the test. So what is the highest percentile you could possibly be? It's a trick question. Anybody know? The highest percentile you could possibly be.
99.
Good. Why can't you be in the 100th percentile? Why is that impossible? Because it would mean you scored higher than 100% of the people that took the test, but you took the test. You can't score higher than you scored. Does that make sense? If you're the highest score, then you scored higher than 99. And by the way, let's say there were 1 million people and you're the highest score, they'll usually say 99 plus, something like that. You can't be in the 100th percentile because that would mean you scored higher than yourself. And that kind of is contradiction. So the 99th percentile would mean you're at the top of the food chain. But percentiles is basically just what you did. I'm not interested in percentiles because it's too much calculating. I have too many numbers. What we are interested in, though, is breaking this up further. The median is technically called the 50th percentile, but I can actually break this down further into what are called quartiles. What do you think that means, quartile? What's the root word here? What do you think quartiles have to do with?
Quarters.
Quarters, exactly. Oh, so I could be the 50%, I could be the 25%, I could be the 75%. Those are all called quartiles. If I'm at the 25%, I'm at the 75%. The 25%, so the 25th percentile. I don't particularly like those words because it sounds like there's too much going on. There's too much calculation. This is called Q1, the first quartile. The 75th percentile is called Q3 because the median is automatically Q2. So if I'm looking at these scores, how do I determine the quartiles? That's actually very simple. Do we all agree in this picture right here, the median is 9? Do we all agree with that? Everybody?
Yes.
Humor me. Say, yeah, I agree with that. Here's how you find the quartiles. Find the median of these 5 scores. Well, that's pretty easy. What's the median of these 5 scores? Wouldn't it be that? Number 4? Everybody cool with that? So that is Q1. What is the median of the next 5 scores?
13.
13. So that is Q3. So in this set of scores, my first quartile is 4. My median is 9. My third quartile is 13. That's it. Oh, okay. Those are really, really useful numbers. I'm going to show you how they're used in a moment. So there's kind of a cool pictorial that goes with this. I really like it personally. But these are how you find quartiles. You start with the median, which is easy because remember, you're dealing with a ranked set of values. And once you start with the median, now you've broken your group into 2 groups. So you find the median of the first group, you find the median of the second group. So you're basically finding 3 forms of a median within the problem. So the median of the first half is the first quartile, the median of the second half is the third quartile. I'm not interested in the 90th percentile or all those. We never actually use those in what we're doing. Now, with that said, there is a picture that goes along with this. Now that I got the Q1 and the Q3, there's a picture. And this is, I love this visual. It does not involve calculation in general. Okay, it does not involve calculation in general, but I can draw a picture. Okay, I'm going from 0 to 16. So that's what I'm gonna do. I'm gonna put, there's 16, because those are my numbers, 0. My median, I want this to be kind of even. Okay, there would be 8 is in the middle. My median was 9. So I'm going to put my median is probably right here. Now, my first quartile was 4. My third quartile was 13, and this would be 4, 8, 12. So 13 would be about right here. Do you agree that my lowest score was a 0 and my highest score was a 16? Everybody agrees with that? My first quartile was a 4, my median was a 9, my third quartile was a 13. I kind of wanted to scale just to make it easier to interpret. This is a visual representation of our data. This in my box is everything from the first quartile to the third quartile, which represents half the scores roughly in general. These are considered more the extremes going the other direction. This is what is called a box plot. A box plot is a very, very simple visual representation when I have my numbers in order. Okay. Now, one of the nice things about a box plot is I start with the median and then I go to the quartiles. And I just basically make a box. It's, like I said, it's not rocket science. And then I go to the extreme ends. In this case, 0 to 16. How many have heard the term outlier? Has anybody ever heard that term before?
Yes.
What you want to try it? What is it? What does that mean to you? If you heard the term outlier, and think of values, make it easy on ourselves. Think of values. What would an outlier be?
Like an exception?
Okay, exception what? In either direction. It would be an exceptionally large or exceptionally small value relative to the others. So if we were talking about income, would Bill Gates be an outlier? His income? I think so, right? If we gave a test and everybody in the class just, nailed it, but one person didn't show up and they got a 0. Okay. Would they be an outlier? Yeah. They're extreme relative to the other scores. An outlier. My closest friend is a statistician. Okay. And he right now works for the University of Colorado at Denver. That's where his family lives. But he was in San Diego for a long time. And he worked for a company that did all of their work contracts with the DoD, Department of Defense. So he dealt with a lot of military statistics. So, naval hospital, stuff like that. And he was telling me that it was really hard because they had to use every number provided. So he'd be dealing with tens of thousands of numbers at a time. Now, the numbers might be something as simple as this. Every single person in the military in Southern California, how many dependents do they have? Okay, that would be a common piece of statistic that he would deal with. So he might have 10,000 different people, and then how many children or have dependents in general, because if they're married or they had kids or both, that kind of thing. And then he's having to do all this number crunching and numerical analysis. But he goes, we would get outliers. And I said, well, what would an outlier be? He goes, last week I'm looking at a guy, he's 18 years old. He just started the military and it has him as having 17 dependents. 18-year-old. He's the Captain Kirk of the military, I guess. He's very busy. 17 dependents for an 18-year-old. Do you think that might be a little odd? Anybody? Do you know any 18-year-olds with 17?
Yeah, that would be. They should only start as R1 recruits.
Well, what it means probably is somebody entered the number incorrectly. It's very unlikely this kid who's graduating from high school has 17 children. It's not impossible, but it's very unlikely. It's probably more the case that he had 0 children, and when somebody was entering the data, they just hit the wrong button somewhere. But my friend said, I can't ignore that. You have to use everything in calculation. So he says there are outliers always. And so in that case, when you're talking about dependence, 0 wouldn't be outlier. A lot of people in the military don't have any dependents, but 17 dependents would be extreme. 17 dependents for an 18-year-old would be probably an error, but you can't count it as an error. You have to actually use it. You say, but won't that make all the numbers wrong? Yes, but when you have 10,000 numbers, having one outlier, one bad number isn't necessarily going to mess everything up. If you had only 6 people, having one outlier is going to mess everything up. Okay, so the idea of a box plot is a simple visual, but the other cool thing about a box plot is it allows you to determine outliers really, really, really easily. So how would I determine an outlier? Okay, what is the range of values right here? What is the range of values from Q1 to Q3? Does everybody see that? It would be Q3 minus Q1. What would that equal? Q3 minus Q1. 13 minus 4.
9.
9. Now, I wasn't the one who decided this, but universally it's accepted that to determine an outlier, we take a multiple of this number right here. This is called, I'm going to write it down, the IQR. That stands for interquartile range. That sounds really impressive. Interquartile range just means Q3 minus Q1. That's all it means. We take IQR, interquartile range, and we multiply it by 1.5. And again, I wasn't the one who decided on the 1.5, but that's kind of the universally accepted value. So if I take 1.5 times the IQR, in this case, that means I'm taking 1.5 times 9. Okay, 1.5 times 9 is 13.5. This is the magic number here. Any value now that is 13.5 or more above this number, or 13.5 or less below this number, that's what mathematically we interpret as an outlier. An extreme. I like when you said that, an extreme value. Yeah, Robert, question?
How did you get the 1.5 for the?
Oh, no, this is sort of the universal statistical definition. Like I said, I wasn't the one who decided. 1.5 along the lines, you know, when they had the Universal Statistic Council, they didn't invite me. 1.5 is this kind of the universally accepted number. You might say, well, I think 2 would have been a better number. Somebody else might say, I think 1 would have been, but we've universally agreed on the 1.5 as the multiplier. Not for any good reason, just seems logical. So when something is way past here or way past here, that's the definition now we have of an outlier. In this set of scores, is there an outlier? This is a simple yes or no question. Are there any outliers in this set of scores right here? I have a low, I have a high, but compared to the other scores, are they extreme?
No.
Yeah.
Well, what's 13.5 past 13? That'd be 26.5. I need a score that was 26.5 or bigger.
All right, I understand.
Does that make sense? We're saying this much past here or past here. So let me do an example where there is one. So in this set of scores, you'd say, no, these are fairly tightly packed. When you have extremes, the problem with extremes in general, they make calculations not really great. It's really hard to work with. Let's suppose that you play on the basketball team and you're an end of the bench person. You just don't get into games very often. So your stat line was, you know, last night you scored 0 and tonight you scored 0 and tomorrow night you're just going to score 0, you know, or what is your season average so far? 0. But then there's a game where somebody got hurt and maybe it was a blowout and you went into the game and you scored 30 points. 0, 0, 0, 0, 30. I think we would all agree that 30 would be an outlier with all of your other scores. You see, every now and then in sports, we see an extreme happen. Somebody does something completely off the charts, have never done anything like that before, and there's no history behind it. It's this unbelievable, incredible thing they did. But we would call that an outlier. Now, what if that you scored 30 and then the next night you scored 30 and then the next night you scored 30? Well, maybe 30 isn't an outlier. Okay, if it happens multiple times. But if I have one ridiculously extreme, we usually think of it as an outlier. So let's go back to this, and I'm going to do one thing. See that 16? I'm going to replace it with 36. And everything else is staying the same. My median is still a 9. Q1 is still a 4. Q3 is still a 13. Everybody agree? Nothing changed except what? I don't even have enough room to put that on there now. Now my high is a 36. Okay. Do I have an outlier now?
Yes, you do. Maybe 36.
Why is 36 an outlier?
It's a huge gap between 3.5.
Yep, because between 13 and 36 is more than 13.5. And we said that's the line in the sand. Question?
I had a really quick question. What does IQR stand for again?
Interquartile range. So it's the difference between your quartiles. So that's like Q1 minus QR, excuse me, Q3 minus Q1, that's called the interquartile range. That's the definition. It's just simply that difference. Nothing complicated. The only reason we say IQR is it's faster than interquartile range. That just sounds so big. Q3 minus Q1, that's the range of values, right? Interquartile means within the quartiles. So the cool thing about the box plot is I can just look at it. In this picture, I don't see all of the scores. I don't need to see all the scores. I see, okay, there's a big block of scores, Q1 to Q3, and there's the high and the high and the lower, and I don't need any other scores indicated. So this is one of the simplest and fastest visuals that tells me something about my values. So if we were doing a measurement, and let's say our class is not huge. We could do a lot of different things to measure this. For example, I might ask a simple question like, how many units are you carrying this semester? And everybody gives me a number. I could say, how many children do you have? Everybody gives me a number and probably have a lot of zeros. I could say, how old are you in whole numbers of years lived? And everybody gives me a number. And you say, well, I'm not expecting any outliers. But every now and then I'll do this one. I've had statistics classes where the bulk of my class is, in the 18 to 22 range. And then I had a retired teacher who wanted to take statistics, 75 years old. And when we're looking at the age, it's kind of cool because you'd see most of the people are right here. And then you have this one person who's way out there. It's a really simple visual that you have an outlier. Okay, that you have an outlier because with age, you could clearly go this way. Would it be easy to get an outlier with age this way? Would that be easy in general to have outliers on the left when you're talking about age?
No.
Yeah, because you don't have as much of a gap between newborn and the youngest person in class, but it'd be really easy at that end to have. Now, let's say that most of you, this was your only class. You're working full time. In fact, that may be the case with some of you. You're working full time. This is your only class. But we could have somebody in the class that's a full-time student. So a great many of you would have maybe between, what is this class? Is it 5 units, 6 units, something like that? And that's what you have. But then you have a classmate who has 18 units. So they would probably be an outlier because the bulk of the group is in here and then you have one person who's way out there. But the box plot is the simplest visual representation. It requires just no work whatsoever. So let's do another box plot example. I want everybody to do this. I like this because of the lack of calculations necessary to answer questions. Sometimes, we have to do a lot of calculations, and I'll keep the numbers down because we don't need lots of numbers to do this. So here's the situation. We have 9, 18, 20, 22, 25, 31, 36, 38, 41, 63. Okay. I would like a box plot for this set of numbers. Now, if I don't get anything else right, here's what I do know. All right. Not that much. I put my low, I put my high. By the way, what's exactly halfway between 9 and 63? What's exactly the halfway point?
31.5.
Between 9 and 63. You did 0 and 63. Take 9 plus 63 and just divide by 2.
27.
9 plus 63. You're doing a difference. Adam. You made $9 yesterday. You made $63 today. Your average was
72.
over
And then divided
2. There
by
we go.
2.
So 36 would be right in the middle. Okay. I want an accurate. Now let's find all of our things. I want everybody on your own, because it shouldn't take very long. I want you to find the median, Q1, Q3. Let's do that first. I gave you 10 scores, so it should be fairly simple for each one of these. The median, Q1, Q3. All right. Does anybody think they have the median? Anybody want to try that? What's the median?
Is it 28?
And you got that by finding halfway between these two? Exactly, 28. Is that a calculation, or can you just kind of look at that? Probably look at it. But yeah, you took halfway between 25 and 31. Now, Q1.
It's 20,
20. Beautiful. Q3.
38.
38. Okay. So what goes in my box plot? That's the left, that's the right, but I kind of like it to scale. Okay. So 20 is probably about there, do the best I can. 38 is only a little past this guy. And 28, again, best I was probably about there. Okay. So again, I would kind of like, 38 shouldn't be right next to 63. That, doesn't really make a lot of sense if 36 is in the middle. So here's my box plot. I am done with the actual picture. That's it. Q1, Q3 median, I have clearly listed. Now, are there any outliers? I don't know. I need to do a calculation. So first calculation, what is the interquartile range? Well, how do I find it? I take the difference of these two numbers. Okay, so what's the interquartile range?
18.
18, 38 minus 20. Secondly, what is 1.5 times the interquartile range? Now use your calculator if you need to. What is 1.5 times the interquartile range? Exactly.
$27.
27?
27. Now am I looking for a score of 27? What is the 27? What am I going to use that for?
Difference between the quarters?
Okay, so this was, this is 38. So if I take 38 and I add 27, that would be 65. If I take 20 and I subtract 27, that would be -7. So here's the way we deem this. Any score that is 65 or more Any score that is -7 or less. Those are what we call our outliers. Again, 27 is a distance. Okay, it's a distance from Q3 this way or Q1 this way. That's 63. We all agree 63 looked extreme. Am I right? Do we all agree that 63 looked extreme compared to everything else? Is 63
Yes.
Is 63 an outlier?
Yes.
No,
We just said we needed it to be at least 65 to be an outlier. So 63, although really high, technically is not an outlier. Oh, that's what this measurement tells me. 1.5 times my IQR, 1.5 times the interquartile range was a number of 27. 27 now is the distance I must travel in this direction or in this direction in order for something to be called an outlier. Okay, that's it. So it's not, you don't have to really make a decision. I mean, 63 is smaller than 65, therefore 63 wouldn't be an outlier. Now, if that was 73 or 100, or, yes, anything bigger than 65 would have been an outlier. All right. So this is box plot. Did we do a lot of calculating? No, but we give a really nice, simple visual. And the nice thing about this is everybody would give the exact same answer because everybody's using the exact same information. Now there's one more type of number that we use for average. And it's probably the one that's used the least often, but it's by far the easiest to come up with. And that is called the mode. The mode simply is the outcome that had the highest frequency, the outcome that occurred the most often. Now, if I gave a set of, we're going to have a 400-point exam. We have 15 people. With 15 people and 400 points possible, do you think we're going to see the exact same score repeated multiple times? Now, we might have lots of A's, lots of B's, lots of C's, but, oh, you got 347 and so did 5 other people. It's very unlikely, if there's 400 points possible in 15 people, very unlikely we're going to see the exact same score. Now, in my example of UCSD, I gave a 5-point quiz to 500 people. Do we see the same score repeated often? Yeah, we had hundreds of occurrences of some of those scores. So if I have more people than I do slots, I'm going to see lots of things repeated. That's great. The mode is the outcome that had the highest frequency. Is that necessarily a good measure of an average? Well, it is in one situation. All right, so here's the situation. You're going to choose your favorite color. And here's how it works. 1 is going to be red, 2 is going to be blue, 3 is going to be yellow. And those are your 3 choices. And so you're just going to write down on a piece of paper 1, 2, 3. Okay, so here's what happened. Here's what came in. And I'll put them in order. We got 1, 1, 1, 1, 2, 2, 2, 2, 2, 2, 2. And then we got 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This is what came in as a class. So should I add up these numbers and then divide by 15 to find out what our group's favorite color is?
No.
Our favorite color is red 0.3. Do these colors have any numerical value whatsoever? They're colors. Do they have numerical value? Does the
No.
color red have a number that, red translates to 6.7? No, it's their colors. This is nominal data. Remember we talked about nominal versus ordinal versus interval versus ratio? These are names. Names don't have any numerical value. So what I'm doing is I'm counting votes. You don't average numbers when you count votes. Which color was the most popular, by the way? Would you say blue was the most popular?
Yes.
Because it got the most votes. So the choice with the highest frequency was blue. Now, I could do this for music choices. I could put down a whole bunch of different music genres and then you vote for the one you like best. We could do this for an election. Candidate 1, candidate 2, candidate 3. The winner of the election would be the candidate who had the most votes, the highest frequency. So in other words, when it's nominal data, just names, you always use the mode, which one had the most votes. Think of it that way. So I do not take these numbers and average them together somehow. That doesn't even make sense because red, blue, and yellow aren't numerical in nature. There's no measurement, they're just names. So this is a fun one. I've known people that did this, and this is kind of silly. I'm going to put, my wife's going to have another child, not really the same. And so I need help from you guys. I need you guys to help me pick out a name. So what we're going to do is you guys are going to submit a whole bunch of different names that you think are really good baby names. So maybe I've got 20 names, 1, 2, 3, 4, 5, 6, 7, and so on. And we're going to come up with this list of names, and then I'm going to have you guys vote on your favorite baby name. And the favorite baby name, the average was 6.7. There's no numerical value for the average baby name. No, wouldn't we want to choose the baby name that got the most votes? So once again, the mode would be the highest frequency. So let's go back to the UCSD example. Or I'm going to do a different one, but a similar one. Okay. So let's suppose we'll keep it simple. Let's say we have a 4-point quiz. So the point you can get 0, 1, 2, 3, or 4. I want it to be a completely new example this time. And so maybe let's say that 8 people got a 0, 14 people got this one, and how about 90 people got this score, 38 people got this, and 74 people got this. Okay. I would like to know what is the median. I would like to know what is the mode. I could also ask for the mean, but I want the median and the mode. I think we all know how to find the mean. I would say 0 times 8 plus, 1 times 14 plus, 2 times 90 plus, 3 times 38 plus, 4 times 74, and then divide by the number of scores. That would be that calculation. But I want to know what's the middlemost score and what's the most commonly occurring score, because that tells me that we understand there's no calculating. So how many scores do I have altogether? 8 plus 14 plus 90 plus 38 plus 74. How many scores altogether? Anybody? Let's add those up. What does that come out to be exactly?
$224.
224. And I can now rank them. I can go 0, 0, 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 2. I can do that. That's not very practical. Cut that number in half. Okay, what's half of this? That'd be 112. So I need the 112th and 113th scores. In order to find the median, because there's an even number of scores, I need the score that's halfway between the 112th and 113th score. Again, because that's half on one side, that would be half on the other. So let's see, that's 8 plus 14, that's 22. 22 plus 90, oh, there's 112 scores right there. Oh, that made it kind of easier. So if we're going top down, right, my score is 7, I'm sorry. Right, I'm gonna go, 4, 4, and eventually 3, 3, and so on. The 112th highest score is going to be a 3, isn't it? Everybody agree with that? If I rank these all the way down, the 112th highest score is a 3. Because there's 112 scores here. What's the 113th highest score? A 2. Again, if I rank these from top to bottom, the 112th highest score, because there's 112 scores here. So if I rank them like this, score number 112 is a 3. Score number 113 has to be a 2. Can anyone tell me what my median is then? Anyone? What's my median?
Just 2.5.
Exactly 2.5, because exactly half the scores are below that and exactly half the scores are above that. I made it kind of convenient. Exactly half the scores are 3s and 4s. Exactly half the scores are 0s, 1s, and 2s. So I take halfway between the 2 and the 3. Now, what frequency do you see the most? What's the largest frequency here? What's the largest number you see occurring? This happened 8 times, 14 times, 90 times, 38 times, 74 times. Cool.
92.
90, the frequency of 90. So what is the most commonly occurring score?
2.
2. So that's the mode. The mode isn't 90. 90 is the frequency. 90 is how many times 2 occurred. 2 occurred more than any other score, so the mode would be 2. The mean, the median, and the mode are rarely the same number, just so you know. It is rare that they would be the same number. And occasionally they are, and when they are, that's actually a good thing, by the way. But they're rarely the same number. So in my example, exactly half the scores were above this, exactly half the scores were below this, and this was the score that occurred the most often. If I want the mean, then I got to add up and multiply by the numbers. That involves a calculator. Okay, so the mean is the only one that truly involves calculation. The other guys don't really involve calculation. So today our main goal was to talk about central tendency and 3 completely different ways to describe a quote unquote average. The mode is not usually very meaningful with a bunch of scores, although you say, hey, more people got a 2 than any other score. That still tells me a lot of information. Okay, if I have a large group of people, a very large group of people, let's say adults, and I said, how many children do each of you have? Then the mode would be that number of children that was the most common. And maybe that number is probably going to be 2. I mean, that's kind of the universal norm. But is that the numerical average or even the middle necessarily? No, but it's probably going to be a really good interpretation. Now, I said mean, median, and mode are rarely the same. There is one situation, and I'm gonna give you a little glimpse of the future. And I drew a picture earlier. Pretend you have a lot of values, huge number of values. So I'm going to draw a curve rather than rectangles. I have a huge number of values. If I have a picture that looks like this has what's called symmetry. It kind of looks like there's a mirror image. You know, it looks exactly the same on one side as it does the other. At least that was my intent. Some of you have heard the term the bell-shaped curve. That's kind of an example. But what does that mean, the bell-shaped curve? If I have a situation where I have all of the values, and this could be like millions of values. I have, ages of people in the United States, everybody. If you get a situation where it looks the same on both sides, then the mean, the median, and the mode are very likely to all be about the same value. That middle value might be the same for all 3. We like it when that's the case. Okay, I get that perfect bell-shaped curve. That's the thing we study a lot in statistics. The situation where I do have this perfect symmetry. Okay, now you can't force it. You actually, when you're doing your measurements, this is a result of it. You don't try to make things fit. And there are a lot of things in reality that work this way. A lot of things, huge. Human heights, for example, tend to be distributed this way, about the same number on each side. One of the ones that we like to study a lot and we use in statistics is the duration of a pregnancy. In other words, whatever the due date is, you might be a couple days late, you might be a couple days early. It turns out that durations of pregnancies have this perfect symmetry. You're just as likely to be 1 day late as you are 1 day early. You're just as likely to be 1 week late as 1 week early. The farther you get, right, the less likely you're going to be 2 weeks. But that's kind of the idea that You have just as likely to be early as late and by the same amount. So we use that when we study things. You know, like I said, human heights tend to look like this, and there's a lot of areas. And so we're going to study this a little bit later in the course. But the idea that if the mean, median, and mode are essentially all the same value, that's actually a good thing. It means it's not skewed. Okay. Does anybody know there's a word for this shape, this type of set of scores? Does anybody know what the word is? Just curious.
Standard deviation.
No, that's a calculator. That's next day. It's called
Okay.
normal. So we say it's a normal distribution. I don't know why we chose the word normal as opposed to like abnormal. When you have that perfect bell shape, that's called a normal distribution. And there are a lot of things in reality that behave this way. And we love studying those things because they're just easier to study. Skewed is harder to study. This is easier to study. Okay, now here's what we're going to do. And some of you got my email. I'm going to go ahead and stop here. I'm going to stop recording. Hold on.